All right, so what I want to do today is I want to focus some attention on the third generation. Third generation is important for at least three different reasons. Obviously, those are the particles that couple most strongly to the Higgs boson, so among the fermions. So we're actually going to measure their interaction with the Higgs boson directly. Another reason they're important is, well, for precisely that reason, they may also be the secret to to the flavor puzzle. Why do we have this weird distribution of quark and lepton masses? Well, it may very well be that for the same reason that these particles are heavy, they also couple more strongly to whatever is the physics of flavor, and maybe we can see that at the LHC. So maybe these particles are not going to be quite the way the standard model expects, because they couple most strongly to something beyond the standard. So they're one of the best places for us to be looking for something a little out of place. The top quark may be the best one, but bottom quarks and taus are also very good. Third reason is experimentally. They're also unique and interesting and worthy of discussion. So that's our plan. Now, before I start, why is it that the tau, the charm quark, and the bottom quark all have about the same lifetime, in the factor of 10 or so? Where does that come from? And why are they short but not so short? Right? The muon has a lifetime that will travel for a long distance, very large macroscopic distance. The top quark has an incredibly short lifetime. What puts the bottom quark, the charm, and the tau in its middle range? Well, they all decay the same way, by emission of an off-shell W. Tau can go to neutrino. We have an E or mu here, or we can have a D or a D and a U. And we get my signs right, so that bar. Okay, so those are the. Of course, this would be a tau neutrino. And whether this is an E or mu depends on whether it's mu here. Okay, fine. So and the charm decays to another quark. It can decay to an S or to a D, also by a W, and then whatever's allowed kinematically can go here too. Now, we already know something about lifetimes from similar processes. The muon decays the same way. What's the formula for this lifetime? Or magnitude? Well, we got two factors of G of SU2. Let me just get the matrix element first. Right, so the matrix element's going to have a G2 squared. It has a 1 over MW squared. That's kind of it. I'm going to have to square that. So we'll make that a 4. Make this a 4. There's going to be some pi's. We'll work that out later. And now dimensional analysis. What needs to go in the numerator?
Mass of the mu.
Mass of mu, because that's the only thing we have in tau. This is essentially massless. All these guys are essentially massless. So the only thing with a significant mass is the muon mass. So let me just put M fermi on the fifth. Because in fact, this is true for all of these decays. There's some heavy god which is decaying to light gods. So the only mass which can appear is a heavy one. Up to some small effects of kinematics, which we'll move on. And then there are various factors in front, but it always goes like the Fermi mass the fifth, just by dimensional analysis. This is the kind of thing you should always, throughout particle physics, almost every answer can be worked up by dimensional analysis, or some simple symmetry principles, or things like that. You should have these things at the tip of your fingers. You can just make an estimate really quickly. Well, that sets the ratio of muon lifetime to tau lifetime. More or less. Okay. There's a little bit of extra stuff because the tau can go to a more final state, so there's a little bit of expanded phase space. Pretty much that's the factor. Okay, so that's why the tau is much, much shorter lived than the muon, even though there's only a factor of 16 or 17 in the mass ratio. The charm quark mass isn't very different from the tau mass. It's got similar final states. The lifetime's not that different. What about the bottom quark? what's different about the bottom? Why is the bottom part, which is several times heavier than the charm part, why does it have the same lifetime? In fact, even slightly more. Ah, yes. What can the bottom part decay to? Well, it can decay to a charm part and an up part in a domain. And there we have a factor of VCB. So we get the same formula, but we were forgetting about the fact that it's not quite complete. There's a CKM factor here for the dominant decay. In fact, there may be a sum of such things. Right? In particular, for the bottom part, I have to combine something that involves VCB with something that involves VCU. VCU is pretty small. Sorry, VB, I said wrong. VUB. VUB is pretty small. VCB dominates, and the square of that's an order 10 to the minus 3-ish, and cancels off the effect of the mass. So it's a little bit of magic, but the ratio of the bottom part mass to the charm part mass to the 5th power happens to more or less cancel off the square of that. There's no obvious reason why that should work, but it does. So it turns out the bottom part is slightly longer lived, and it's particularly convenient that it's the longest lived of the 3. Because of the 5 quarks that are lighter than the top quark, the jets that are produced by up quarks and down quarks and strange quarks all look pretty much the same. The ones produced by gluons, again, pretty much the same, a little fatter, but only on average. But charm quarks, and especially bottom quarks, have a special property, because the meson that contains that bottom quark or that charm quark, which is generally the only meson of its type inside that jet, has a lifetime that's long enough that with high precision measurements, you can see that it's actually moved relative to the collision point. So you can identify, statistically, but with pretty good accuracy, a jet that has a bottom quark in it, which is great if you want to study properties of the bottom quark. Okay? So the lifetime of the bottom quark is such that, especially when you account for a boost factor, if its momentum is pretty large, it may travel 100 microns, millimeter, even a few millimeters, even a centimeter. Well, someday we're going to see these things traveling several centimeters if we get the energy up and up and up. But it's not unusual to have this thing travel that sort of distance. Now, what kind of a distance are we talking about relative to what? Well, let's look down the beam pipe. Collision occurs right dead center here. And I've just drawn the beam pipe for you. There's a beam pipe that keeps an extremely perfect vacuum, 13 atmospheres. That's really, really good. You do not want a lot of gas floating around inside the beam pipe. The protons will keep hitting it, and that will degrade your beam. So the beam pipe has an extraordinarily good vacuum, and so they don't, well, it's not too big, a couple centimeters. So normally when I produce a jet, various particles come flying out. This is what I'm drawing is what actually happens. Of course, this is not what you measure. You don't see that. You only see what happens when a particle comes in contact with your detector material. Right? So what you see, as an experimentalist, is that you have some detector material in layers out here. And that's not quite the scale. I guess I should really say, well, there's one here, and then there's going to be one here, and then there's going to be another one way out here. I mean, you know, there are these layers of tracker material. And so what you're actually going to see is this track leaves it here, and then it leaves it here, and then it leaves it here, and this one leaves it here, here, and here. This guy's a neutral particle. It doesn't leave any information in the tracker. And you get another one here, here, and here. The underlying event is throwing stuff everywhere. There's pile up, so there's random hits that just happen to show up in various places. You've got to deal with all of that. You have, at CMS, 9 layers, I think, 8 layers. And Atlas is more complicated because they have this funny piece of thing on the outside of their tracker. But roughly speaking, you've got to connect the dots from. And so you try to find strings of hits and draw lines through them as best you can, and hopefully that corresponds to the truth. And this is where it's really important that the inner layers, well, I shouldn't say quite that strong. Obviously, the more resolution you have in the inner layers, the better you are able to tell the difference between a track that did this and a track that was produced by a particle that traveled a small distance and then decayed. So that when you follow this thing back, now it's not drawn very well, but I think you understand what I'm trying to say. It misses the collision point. So you're looking for tracks that miss the collision point. That is a sign that they were produced by something that was somewhat long-lived. Okay, and that's, well, what is a jet that is proposed to be a jet that has a bottom quark in it? It's a jet that has something like this going on. Because that doesn't happen in up quark and down quark and strange quark jets very often. So, a track which is displaced, whose extrapolation misses the collision point. A displaced track is what gives rise to a B tag in a jet. You say, well, that jet's probably a B jet. Of course, you don't know it for sure, but that's what you're looking for. Now, this is where it's important that, in comparison to previous colliders, these trackers are much more detailed. And I'll say a few more words about that in a minute. For charm quarks, you have the same opportunity, but the lifetime is about a third as long. So you will sometimes get displaced tracks from charm quarks. You'll even get them from towers, if they're sufficiently high boost. So, but the majority of things that you see in this form are going to be these. Okay. Let's talk about towers in a little more detail now. We'll come back to these. Right, the tau is a very interesting object experimentally and complicated because a tau can do 4 different types of things. So tau can decay to an electron and a neutrino and an antineutrino pair. And roughly speaking, the electron carries a third of the tau momentum, but of course sometimes more, sometimes less. And this happens about, I think it's 17% of the time. We decay to a muon and some neutrinos, neutrino and antineutrino, another 17% of the time. And the rest of the time it decays to hadrons. There's 2 interesting classes. So it decays to hadrons and of course 1 neutrino. Tau still goes to neutrino. And then the W, off shell W goes to quark, antiquark pair. The quark-antiquark pair might give you a rho meson or a few pions. But in general, either there's 1 charge track and some number of pi zeros, which might be 0, 1, 2. Or you get 3 charge tracks plus some number of pi zeros. And this happens about 50% of the time. And this is the remainder, which I guess is another 60 or 50%. Did you do that right? Collectively, these are called 1 prime because they contain 1 charge track. And these are called 3 prime. Now, how do I distinguish this from an ordinary QCD jet? What's different about it? There are two features that are different. How many tracks in a typical QCD jet of 50 GV? Put that thought on the board. 10-ish is not an unreasonable number. It's not 1 or 3. It is unusual, not unheard of, but it is unusual for a QCD jet to have 1 or 3 tracks. That's not enough. It does happen often enough that there would be a lot of fake tails for that. There are enough fake tails anyway. But there's a second key feature which is different. And I haven't really emphasized it, but you've sort of seen it, and I did sort of say it in words, which is that the invariant mass of a jet is not 0. You get a spray of particles. And the invariant mass of a jet is something that increases with the momentum of the jet. Slowly, but it increases. So that a 100 GeV jet may have an invariant mass of 10 GeV or 20, even 10 is not unusual. And it'll just keep going up as the PT of the jet, as the momentum of the jet keeps going up, but the mass will go up slowly with it. This thing is constrained by the fact that it literally came from the decay of a particle whose mass is 1.77 GeV. So these particles that you observe as tracks, plus any energy that came from these by zeros, when you sum it all together, can't have an invariant mass larger than 2 GeV. So compared to a typical jet, it's extremely narrow. Right? So what that really means experimentally is that if this is the collision point, you'll see your pi minus, let's say, in this one problem case, curving in the magnetic field. But aligned with its initial direction, when you reach the electromagnetic calorimeter, will be a very narrow spike of photons from the pi zeros. So that is a very unusual jet, and that's the sign of hadronic tau. Very narrow jet. This is what people will usually call a tau H, a hadronically decaying tau. Again, it may be 1 prong, it may be 3 prong, but it's always very narrow, and a sign of it is that the charge tracks are few and collimated, and any additional electromagnetic energy, which might be 0, by the way, you could have 0 places, you could have no places. Any additional energy would be very collimated. And those things make it unusual enough that, especially with the high quality detectors that we have now, the LHC, the probability of a jet to fake tau is not that high anymore. It used to be pretty darn high in the previous colliders, but these machines are pretty amazing. How do I tell the difference between an electron and a muon that came from the tau and one that didn't? Trick question. I can't. Okay. I can't see the neutrinos. I can't be sure. If I see some missing energy, I can't in general be sure that it came from neutrinos that came from there. So in general, I just don't know. That's just something I have to deal with. So hadronic taus are tricky in that they have big jet backgrounds that you have to deal with. They've got a lot of fakes, but they are kind of unique. Whereas if you see an electron, you really don't know if it's an electron that was produced directly, let's say from the Z boson, or one that was produced first through a tau. Okay, any questions about taus? Good, let's see if the Higgs boson decays the taus. So, that's what we're looking for, and we have to account for all of these possibilities, which you notice there isn't a dominant one. So if you want to do a good measurement, unless it turns out that you're really sensitive to one and really insensitive to all the others, you're probably going to want to do all the different measurements and then try to put them together at the end. Not that easy to do. Okay? Good. Let's see. So, here's an event. This is CMS. What do you observe here? Well, what's this? That's a muon, right? It goes all the way through the detector, hits something way on the outside. Okay, that's the way they'll represent a muon. What's this? It's trickier. So what do you think the red and blue indicate? It's not the muon system, it's not the tracker, so what must it be? We have calorimeters, right? So presumably one is the energy, one calorimeter, and one is the energy of the other calorimeter. Okay, we've got to figure which is which. The important thing is you notice there's only one very straight track pointing at this jet. This is a jet, right? It's got electromagnetic, and it's not photon. It's a photon will only have electromagnetic energy, same with electron. So this is not an electron. It's not a muon because it doesn't go through. It's not an electron because it's got energy in both calorimeters. Therefore it's a jet. But it looks like it only has one very hard track pointing. It's a little hard to tell. This is some sort of, it's a two-dimensional representation we'll talk. But that's basically what they're showing you here. There's one track. And the energy is actually quite narrow compared to the typical jet. That's hard to tell from this picture, but it's true. So this is a candidate for a 1 prom tau. And therefore this is a candidate event for a tau plus tau minus. Presumably they measure the charge from the curvature of the tracks and they have opposite charge. So this is a tau plus tau minus event, maybe, maybe not. And it probably doesn't come from a Higgs, but it might. So now we've got to figure out if we have more of these than we expect in the absence of a Higgs. If we have the right number, we expect in the presence of a Higgs. All right, let me show you the answer, and then we'll work backwards to sort of figure out how they got it. Again, this is CMS's answer. Ignore the plot on the right. Let's focus on this one. Now, you may recognize this strange label from what I showed you for the photons. This is some sort of combination of things. So what's going on? They're making 4 measurements. They're making a measurement where the 2 taus give them an E and a mu, an E and a hadronic tau, a mu and a hadronic tau, or 2 hadronic taus. And then they're weighting them and they're combining them together. So this is not the raw data, it's already been very much processed. Let's not worry about that for a minute. Why do you think they didn't do EE? Or mu mu? Second?
That comes from
Well, so can you be more precise? I mean, I don't know that this E mu came from tau tau either. So what's the issue with EE and mu mu? It's similar to something we did yesterday. Same issue. Remember that the WW measurement was made with E mu and not with EE and mu mu? Why?
Yeah, lots of Drell-Yan.
There's background. There's more background. Okay. So Drell-Yan in general, even just Z bosons going to EE, cannot necessarily be distinguished from sometimes a Higgs goes to tau tau indicates from there to EE. So it's just more background in that case. Whereas it's much less likely if Z does not go directly to E mu. So the only way that a Z boson can give you E mu is if it first decays to taus. But then it has to decay, both taus have to decay to electrons, and the probability of that's not so high. So it's much more likely that a Z, if it goes to 2 electrons, did so directly rather than through 2 taus. So the backgrounds are considerably smaller if you're focused on this final state. Now, all of these have background from Z bosons. The Z boson can decay to 2 taus and they can give you all of these things. And that's why there's this giant peak here from Z goes to tau tau. Notice the other backgrounds that are important here. This one called electroweak is actually W plus jets, most of it. I'll come back to that in a second. And then this one is QCD. All right, so what do you think the QCD one is? What is QCD going to give us background? How does QCD give us backgrounds to this? Or any one of us? Let's start with tau H, tau H. How can QCD give us a background to 2 hadronic taus? What's hadronic tau? It's a weird looking jet. QCD gives two of those. QCD gives us lots of jet pairs. Lots and lots and lots and lots of jet pairs. And the probability that two of them are weird, fortunately, isn't huge, but it's not small enough that you can completely neglect it. It's there on the plot. Do you know how they, okay, so we're going to go into a little more detail now than we did in the last one. How do they figure that out? How do they figure out how big it is? That's tricky. Okay, so imagine you're an experimentalist. You got a problem. You are not sure that the QCD is small enough as a let's pick a relatively easy one. Let's take mu tau h. Okay. So you're looking at events. Now I'm teaching you this because you really have to understand how experimentalists think about problems like this in order, again, that you can propose good ways to search for new physics. You have to understand what they're dealing with and how they approach it. So their problem is they're looking for a signal that, let's say, has a muon and a tau h in it, a narrow jet with a single prong or three prongs. How can QCD give me something like this? And more importantly, how am I going to figure it out? Because that's a very rare thing. My Monte Carlo isn't going to predict it correctly. Monte Carlos are good for getting the bulk of things, getting something way out on a tail where all sorts of things have to go wrong at the same time. You can't get that from a computer program. You have to get it from your data. So how are you going to do it? So here's the trick. Right, we're looking for something where, let's say it's a mu minus and hadronic tau plus, right, pi plus, or vice versa. But when QCD fakes a tau just by having a weird jet over here, or when, let's say, there's a B quark over here and the B quark or charm quark and it's decayed produces a muon and somehow the rest of the jet disappears, there's not much correlation between it happening on this side and happening on that side. Nor is there much correlation between the charges. You would think I'm equally likely to make a hadronic tau plus and a hadronic tau minus fake from a QCD jet. I mean, if I have a gluon jet, it doesn't even have a charge. For instance, so I'm just as likely to get tau plus as tau minus in my fakes. And similarly with muons. Because I get bottom quarks, I get anti-bottom quarks. I get charm quarks, I get anti-charm quarks. And they'll fake things, sure, but with equal probability for the sign. And these are uncorrelated in the QCD background, and therefore, to measure the QCD background, I look for mu minus, tau minus, or mu plus, tau plus, which don't correspond, obviously, to my signal, or to my other backgrounds. It's not very much. And they do correspond to a source of phase. So one way to measure this is to look at the same sign, tau mu, or same sign tau tau, because QCD is likely to do same sign as opposite sign, whereas the signal is not. So that's one trick. How about this one? This is lecture week. I said it's W plus jets. Well, they've got a trick for that, not an obvious trick. Their trick is to use that variable I mentioned last time called transverse mass. Here's a plot of various backgrounds that produce a mu and a hadronic tau as a function of the transverse mass, because there is missing energy in these events, right? The signal is from neutrinos, the backgrounds could be from neutrinos or from fakes or from all sorts of things. But if it's from a W, the W really has a neutrino in it. So these events really have a signal that there's a W in there. And so W plus jets, if the W produces a real muon and real missing energy, and then some random QCD jet produces a fake tau, is going to give you an MT distribution that falls off around 80 dB, like we saw last time. What's less obvious is that the QCD background and the Z goes to tau tau background fall off before you get there. So by the time you get around here, this distribution is dominated by the W. Now, I left out something. I should have said this. To make this plot, they don't use precisely the same events they use over here. They'll use a slightly different choice. One that has the property that I just described. By the time you get out to here, you have a place where you can make the measurement of the W plus jets independently of everything else. It's not contaminated by these other backgrounds. So the trick that they use again and again and again is, if you want to understand what's going on in your signal region, you look for a control region, a slightly different set of events, where one of your various backgrounds dies. You take the Monte Carlo that you use to predict those events, and you check and make sure that it works in the control region. But if it doesn't work in the control region, you don't know what you're doing. So you have your Monte Carlo, and that's fine, but you never entirely trust it, because it was written by theorists. You're an experimentalist, you don't trust theorists. And you're right, because these Monte Carlos are complicated. There's all sorts of stuff that could go wrong. And often the normalizations are wrong because, for example, they were calculated the leading order. The next leading order calculation isn't in yet, so the normalization is probably wrong. But you check to make sure that you match things correctly. In fact, in this plot, probably what they did is they ran the Monte Carlo, and it probably came out too high or it probably came out too low, and they adjusted the normalization to fit the data. The Monte Carlo doesn't always work. You adjust it so you fit things in the control region, and then having adjusted it, now you can use it in the signal region. With some uncertainties in that process, which go into your systematic error.
How do you adjust?
Second?
How do you adjust? That's how you adjust.
Well, a Monte Carlo has many parameters in it. One of the most obvious is an overall normalization. So that's the easiest thing to check. But Monte Carlos have other things in them too. There may be some treatment of, there's always some treatment of the underlying event or pilot. There are parameters that control how jets work and so forth. Now, some things you don't want to change in one place and not in another, right? There should be some self-consistency. But here, for example, can I think of one that's sort of obvious? Here, probably it's just the normalization they would have adjusted. I can't immediately think of something that they would also adjust out here. Probably, you know, without reading the paper carefully and seeing exactly what they did, it's hard for me to guess. I want to give you the general point, which is that there's always a control region, and the control region is used before a measurement is done, and it's a background is simulated in the signal region. So when you read those experimental papers, they're going to describe that, and that's what they do. What about the Z? The Z is another case where, well, you could have a Monte Carlo, you could run it, you could have a control region, signal region. What do you do? Well, here the trick is, you really don't need the Monte Carlo much at all. Because you're interested, your background is from a Z boson being produced and decaying to taus, plus anything else that might happen in the event, extra jets. PT of the Z will be different depending on the event. Its rapidity will be different. It's a whole distribution of events. How are you going to model that? Well, you know enough about the Z to know that its decays to leptons are flavor universal. You measured that already. So you know, even without assuming the standard model, you know from data that the rate for it to be this, plus the exact same stuff, plus the extra jets, with the different rapidities and the different PT distributions, it's exactly the same. So if you measure this, you've predicted this, and you know enough about tau decays, if you're really careful with all the spin correlations, and you measure them very carefully, the polarization of tau is important, then you can predict, for having measured this, what the distribution of E mu, E tau H, mu tau H, tau H events are going to be from the Z. And you never have to use a Monte Carlo that tries to predict this distribution. Experimentalists love that. Because different Monte Carlos disagree with each other. Here you don't have to worry about it. You always have to worry a little bit. There's always something. Okay, this is the basic principle. When you're dealing with the Z, going to taus or going to neutrinos, use the fact that you have the Z going to muons and to electrons. You can make measurements and then bring them home. So that's what goes into this plot. Those are the three major backgrounds. And now the data goes on the page, goes on the plot. After you've done all of that, now you can put the data here and, well, there's a little bit of an excess. Oh, I left out one thing, very important. What is this a plot of? M tau tau. Why would this peak at the z mass? Right? If the z decays to an e and a mu and a bunch of neutrinos, how do I figure out that came from z at all? I didn't measure the neutrinos. It's another trick. A very clever trick, due, I think, to Frank Page. But I could be wrong with that. I believe he's responsible. So, this is just one of those things that makes you realize, sometimes have to think of something very simple. So, it is true. Let's take the case where our taus decay to an electron and an antineutron. Okay, and I'm looking things down the V pipe. So this is actually the way the event looks. So there's probably some jet swimming off this way to balance the momentum. Okay, what do I actually measure? Of course, there are neutrinos that went this way and this way. I don't measure those. What I measure is the total missing transverse momentum, which obviously points, something like this. So I've measured the electron energy, the electron momentum, the mu momentum, and the transverse missing transverse momentum. Here's the trick. You don't know where the neutrinos went, but you know that some of them went this way, and some of them went that way. So you know the angles, you know the directions in which they went. And that's enough information that as long as these particles are not back-to-back in the transverse frame, you take this momentum and you say, well, it has to be a sum of a vector that's this way and a vector that's that way, and it turns out that has a unique solution. So in fact, in this case, you can reconstruct the tau momenta completely, just assuming that the only neutrinos in the event are ones that are collinear with the electron and ones that are collinear with the mu. And once you know the two tau momenta, you know the invariant mass of the taus. And it works. There's the z. Doesn't work perfectly, it's kind of wide, but it works. Exercise, try it at home. Confirm that if you know the directions the neutrinos went and you know the sum of their momenta, then you can work out the momenta of the taus.
Is it reasonable to assume no more neutrinos?
Say again?
Is it reasonable to assume no more neutrinos?
To assume no more neutrinos. Well, in an event like this one, it would be perfectly reasonable, right? Similarly, if there were QQ bar goes to Z, well, let me be more careful. So here's the event. QQ bar goes to Z, the Z decays to taus, there are neutrinos here. Now, what else is there? There are jets. What's the issue? First of all, a jet might be a charm part jet, and then it might contain a neutrino when the charm part decays. Even more likely, jet measurements are not perfect. So the missing transverse momentum suffers from the fact that at the very least, your measurements of the jets are not perfect. And that's why this is not extremely narrow. That's why the resolution here is good. The basic idea works. And in particular, you expect the Higgs to be dominantly sort of, in this range, around 125, right? So let's see, this is 5 bin, 2, 3, 4, 5. So the Higgs should be somewhere in this zone. It actually turns out to be just a little below 125, when you read it carefully. And, well, you can barely see this here, but notice that the error bars are very small, because the number of events is very big. So, to help the eye, what they've done here is they've done a subtraction, which both makes things look better or worse than they are in certain senses. So what they've done is they've taken the data and they've subtracted it from the background prediction in the absence of the Higgs. And what's shown in gray dashes is the uncertainty in the background, which is, I'm actually not sure what dominates it, I forgot to look that up. And it's big around the Z peak, but it continues all the way down. It's hard to see probably for you, it kind of does this. And then in red is what you should see from the Higgs, and that's this part. Okay, and is this just a sign of uncertainty, or is this a sign that there's really something there? Well, they will tell you it's statistically significant at a couple of sigma, that there's something there. At some point you have to trust them. And you trust them in part because this is not the only plot they make. And this plot may be hard to see, but they have a lot of different things that they look at. And that's how that measurement is done, and then yeah, they do see something. Okay? Any questions about Higgs goes to tau tau? It seems to be there, which is nice. Now we know that this Higgs interacts with leptons, which we didn't know before. By the way, the tau tau measurement is famous because it was important in convincing, in the case that CMS made back in December of 2011, that they really were seeing signs of Higgs, and it completely went away for June of 2012. In fact, it was a deficit, I believe. And then it came back. Well, this is, again, data fluctuates, right? Don't make too big a deal out of 1 and 2 sigma effects. They may go away. They may come back. This was a nice thing. But now it seems to be permanent. There's both Atlas and CMS. Okay. Let's move on to bottom quarks, unless there are any questions about this. Okay, so if we see a jet in our detectors that has the property that it has, as this one does, maybe some tracks that don't have any displacement from the origin, and some tracks that do, it's a good chance it's a bottom quark jet. Of course, it might just be a mistake. There's all this stuff flying around in there, and there are fake tracks occasionally. And a fake track, obviously, has got some chance of not going, if it's a fake, it may point anywhere. And if it's a charm quark, it may do this occasionally. So, how do we make sure we get bottom quarks? The answer is we can't. But fortunately, the numbers work out. It's not obvious. You have to actually look at how often these things happen. Partly because these detectors are really, really good. And partly because the bottom quark lives long enough. If, and this is very crude, if somebody says, okay, I have what looks like a bottom quark in my jet, then, actually let me say it differently. Better say it this way. If a bottom quark is produced with not too low momentum, not 10 GeV, not too high momentum, not 1,000 GeV, but kind of in a sweet spot. So a B quark, let's say 40 to 400 GeV. That might even be a little too high, but that's kind of the range. Maybe 200 would be safer. The higher you go, the harder it is to do this eventually. The probability of tagging it, that is to say, the probability that the jet that it produces will appear to the detector to have a B meson in it, signaled by this displaced track or two, is more than 70%, which is pretty darn good. It can even be better in some cases. At the previous colliders, it was 40 to 50%. I think everybody was surprised they could do this one. This is, again, a sign of how good these detectors are, and especially the fact that they chose not to use strips of silicon, but pixels of silicon, where they're getting very detailed three-dimensional information on these hits. It's really important for them to put that in. It made a big difference in this process. Now, supposing instead it's a charm quark, well, then the number is maybe 10, 15%. And supposing it's an up or a down or a strange quark, well, then maybe we're looking at numbers like 0.5%. A gluon is very tricky for the following reasons. Unlike anybody else in here, a gluon has a reasonable probability that it will split into a charm quark pair or to a bottom quark pair. So you have to be very careful. You're talking about the gluons that don't split, you're talking about all gluons, when you talk about how likely you are to tag it or not. So strictly speaking, a gluon that doesn't split would be much like these guys. A gluon that splits to charm be like this, except for the fact that its probability of splitting to a charm anti-charm pair is not that high. And the gluon that's supposed to be B bar will be like this, except that its probability of splitting is even lower. So they're competing effects, and you have to talk to experimentalists and make sure you get it right. But that's a subtlety which has tripped theorists up in the past. So make sure you know when the experimenters tell you how likely they are to tag a gluon, they're usually talking about the gluons that don't split. Now, these numbers are not hard and fast for two reasons. One is they depend on the momentum of the jet, they depend on the direction of the jet to some degree, and they depend on exactly how they do the tagging. It's not just that they look for displaced tracks. They look for displaced tracks that are kind of characteristic of B mesons and less characteristic of charm mesons, because they were interested in B's more than charm for many measurements. For example, if they're looking for top quarks, they're interested in B meson and not more than charm. So I've greatly simplified what they do. And whatever they do, there are a lot of different ways to do it. So if they can play all sorts of games, sensible games. They can say, well, it's more important for us in this measurement, let's say, to get as many of the B's as possible. So we'll use criteria that are rather loose. We'll be very generous. We'll collect as many B's as we can. There'll be a price for that, which is they'll collect more charm. The fake rate, or like the tag rate for charm, will go up as the rate for tagging B's goes up. And so the mistag rate. If instead it's critical in their measurement that they have a really pure sample of B's, you don't want any light quarks in there, they don't want any charm quarks in there, well then they'll work much, much harder. The tagging rate will go down to 60 or 50%, but maybe the fake rate will go down to 5% here and 0.3% there. So it's not a fixed number, it depends what they choose to do, and they will, for each measurement, choose something that's optimized for that measurement. But this is the rough zone of coming. And again, at very low momentum B quarks, it's hard to tag because there aren't that many tracks. So we track, and then at very high momentum B quarks, these very, very narrow jets, and it can be hard to pick up the individual tracks. So that gets there's other issues there too. But there's sort of a sweet spot in this mid-range where they're doing amazing work. Okay. So how do we find the Higgs boson decaying to bottom quarks? It's the next thing we want to do, right? This is hard. I told you where it was hard. If you just make a plot of the BB bar invariant mass, when you take all the events in that you've discovered in your detector, the LHC, that have two jets that are B tagged, and you plot the invariant mass, right? So we try to do something like we did for the photons. We just make plot of M, BB bar, okay, and we look for the signal. I don't even think I can draw the signal on here. For two reasons. One is it's small compared to the background, and the other is BB bar invariant mass isn't measured very well. Because it's made out of two jets. The jets are not measured at high resolution. So the resolution, in contrast to photon resolution, which is in the 1% range, is more like 10%. So you're taking this peak and you're spreading it out. So even though the Higgs goes to bottom quarks 2/3 of the time, that's quite a few events. The backgrounds are just going to kill it. No hope. In fact, we don't even easily observe, we don't observe the Z boson decaying to bottom quarks, and it's produced more often. Well, strictly there's a way to do it, which I'll describe in a minute, but there's no direct way to measure it. So how do we go about finding Higgs goes to BB bar? We need something that makes the event more unique in its appearance. What else can we play with? Well, one that we might think of is to study the Higgs when it's produced this way. When I get a couple of extra jets, and these are very interesting jets. I'll come back to them in a little while. Let me just say for the moment, these jets are not like other jets. This is a particle that came in and emitted a W and just got kicked a little bit sideways. So it's a momentum, it's a jet which tends to be very far forward, or backwards, I don't know what I mean by forward. In other words, it's a very large eta, typically. It's not like a jet which goes in the center of the sector. It's a jet which has relatively low transverse momentum and a heck of a lot of energy. And you've got two of them, one on each side, one from each proton. So that sort of characteristic is sort of interesting. All right, you can look for a BB bar tear in the center of the detector, and jets very close to the B pipe, one in this direction, one in that direction. Well, that's not quite enough in this case, but we're going to use that later for other methods. The thing which turns out to be better.
Sorry, I don't understand what you mean.
Yeah, okay, go ahead.
I don't understand what you gain with that. What would you gain with this?
Well,
It's why is that the background?
you have to convince yourself that this happens more often in this process than it does in QCD. And it's not entirely obvious. We will come back to this. There are cases where you can really. I just wanted to all I want to emphasize here is that there is something interesting in this production process that's not present here. Here you may get extra jets, but they're not necessarily close to the B pipe, because here intrinsically they tend to be. How close they are, we'll have to go into details. And there are other interesting features we'll come back to. This one, however, where we have a W or Z plus a Higgs. And this leads to 1 or 2 leptons. Now it's getting interesting. Because QCD doesn't do that as often. So now we start looking for an event with 2 bottom quarks and 1 or 2 leptons. And that brings the backbones down a long way. As you know, having a lepton already brings things down by a factor like 10 to the 6. So now we're starting to be business. It's still not easy. Here is a plot. Again, it's weighted events and so forth. But roughly speaking, it's the number of events where what they're plotting is the number of events weighted in some way. This is CMS data again, full data set, against the invariant mass of the 2 jets, which are BTAG in this case. So what they're doing is they're taking events with, they look at events where they've got 2 jets which have some sort of displaced track. And in this case, they've actually combined the events that have 1 lepton or that have 2. Probably should have just shown you a plot with one or the other. That's a little bit confusing. But basically, that's why you see Z plus BB bar and W plus BB bar contributing to significant backgrounds, because they've combined these together. Right? And that's not surprising that this would be the dominant background, right? You produce a Z, and then QCD just gives you gives you a bottom quark and an anti-bottom quark there. Why not? Right? So you draw your Feynman diagram. We have a blue-blue collision, and we have B bar, and we spit off the Z. Okay, there's a background. Or QQ bar produces a W and spits off a gluon, which is off shell and turns to BB bar. And these are substantial backgrounds, and you have to account for them. And they're not entirely reducible. Okay? And they're big. But what they've done here is they have used the fact that the Higgs when it's produced, is often produced with a somewhat larger boost than these BB bar pairs are. And so they've used that to try to reduce the background a little bit. I'm not going to go into detail on this measurement. We can certainly take a look. But let's make sure we understand all the backgrounds after they've done it. So they've played some tricks. Okay, so now what have they got? They've got Z plus BB bar, and then what's this? Z plus UDSCG. Huh? What does that mean? So, this is a case where one of the B tags picked up charm or some quark that wasn't charm or quark. Right? This is from the mistagging, the tagging of something you didn't want tagged. They're demanding a couple of tags, so, but still there's some background. Same with W plus UCSCG. So demanding 2 B tags, you mostly have the background that you expect, but you have some additional background for the fact that your tagging is not perfect. That not only don't you tag all B's, but sometimes you tag something that's not a B. It's probably mostly charm in this case. Then there's this big one. TT bar. Why is TT bar important?
Now it's 2 B's.
Right? TT bar gives you 2 B's, what else? Give you 2 leptons, which is our signal, right? We're looking for, let's say C goes to 2 leptons and 2 B's. Now, it gives you something else. It gives you missing energy, because their neutrinos are around. So you probably want to demand, if there are 2 leptons, that there not be very much missing momentum. That will tend to reduce the background from the top. The top is a big background to this signal, because it gives you 2 leptons and 2 B's a lot of the time. About 4%, 5% of top quarks will give you EE BB bar, or mu mu BB bar, or E mu BB bar. This signal is only leptons of the same flavor, right? If I have 2 leptons, they're coming from the Z. So they're either EE or mu mu. Top quark gives you that, but it also gives you E mu. Now you know you measure it. You don't need a Monte Carlo. If you want to measure this background, go measure it in the case with an electron and muon. That will come from top, but it won't come from your signal. Nor will it come from this background. Tricks, always tricks. There are things that top quarks do that Z bosons don't. Sometimes you use it one way, sometimes you use it the other way. Here in this case, your signal is leptons of the same flavor, so you measure top quark in a sample of events where you have an E of mu. And then you can put it on this plot. Is that clear? I see some confused faces, but I'm not sure exactly what you're confused about. Can anyone formulate a question? In the process of doing this sort of theoretical work, providing the experimentalists with a trick is often as valuable as providing them with the rest of the strategy. So if you can say, yeah, but this looks like it's really hard to do, but here's the trick, here's how you can actually do it. That turns something which is a vague idea into something practical. Well, that makes a difference in a measurement being made and not being made. So this stuff is very important to the process of actually figuring out what can be measured. The tricks involved often result in a reduction of the systematic error on some background, from maybe a factor of a third to a factor of 10th. Well, that makes a big difference. I mean, you can imagine, try trying to detect this kind of excess if your error on that part of the background is 50%. You can't do it. So you have to come up with these tricks. They're part of the process. You're looking, and this is true not just for the Higgs, but because nothing spectacular has shown up at the LHC so far, anything that you might want to pull out of the 7 or 8 TV data is probably going to involve these subtle effects, making these tricks even more important. And the high precision next to the memory calculations increasingly important. And the same will be true with the 12, 13, 14 TV LHC that we're coming into. If nothing spectacular shows up in the early days, it doesn't mean there's nothing in there. That means we got to buckle down as theorists and help experimentalists come up with every trick in the book to get their errors down so that we can make the precision measurements that will reveal subtle things. You can't do it, you've got this great, if you can't do it, then you have this great machine, but you can't learn anything. So it's very important. Now, the really interesting thing on this plot, which you may not have noticed, is this. VV is another word for WWWZZ. And that contributes to this signal. For example, W plus Z, or Z plus Z, can give you 1 or 2 leptons plus BB bar. And of course, the BB bar likely comes from the Z. The W doesn't go to BB bar. So you expect that BB bar pair to sit around 90 GeV. So two things you can notice. So first of all, here's that signal. Okay, that's not our signal of the Higgs. The signal of WZ or ZZ is here. It's this gray line, and of course it's superposed here. It's easier to see it down here. And you see how wide it is. Okay, that's because you don't measure BB bar invariant masses very well. That gives you a sense for how well it can be done. So that's the Z boson, if you like, in WZ and ZZ events. WZ equals to BB bar, and they observe it. Right? You can see it's there. Because they've got all the backgrounds under control, they can find it. Now, it's very important that they can find W plus Z, or Z plus Z, because if they couldn't do that, do you think they could find W plus Higgs? Which is a smaller signal. No. So this was a very important test of the method that they could find this. And having seen this, we're now a lot more confident that this smaller signal, here it is down here, this is the signal of the Higgs, and here it is superposed. We're a lot more confident that at least they understand their backgrounds pretty well. The measurement is being done well. And again, they claim they see a sign here, right? I mean, well, okay, this point's a little bit low compared to the expectation. This one's a little bit high. You add them together, you account for some other things. And the claim is that, again, some sort of two-signal-like access. It's consistent with there being the Higgs going to BB bar. Not yet something you could say would convince you on its own. There's no sign that it's absent. So it doesn't look like the BB bar fraction of Higgs decays is wildly enhanced or wildly suppressed. Any questions about that? This isn't the most updated set of plots, and there are a lot of different versions of these plots. These are really here to give you an example of what you should look for. On the left is Atlas, and on the right is CMS. And what's shown here in various ways is what they've measured in gamma gamma, 4 leptons, WW, tau tau, and BB bar. And in this case, they've broken it up, and I'll say a little more about that in a moment. And again, this is not up to date. This Atlas result is updated, this Atlas result is updated, even this one is updated. These two are the full data set, and these others have changed a little bit. You see a couple of things. So, for a mass of 125.5 GeV, remember, the branching fractions and cross-section depend on exactly what mass you choose. For that particular mass, this is the standard model expectation at 1, by definition. And this is what they measure relative to that. So they measure a ZZ rate that's a little high, by a little over 1 sigma, a gamma-gamma rate that's high by almost 2 sigma, and a WW rate that at least is large enough that you can pretty much convince yourself it's probably not 0. But you don't have to really verticalize. And at least at this point, the tau and B's weren't convincing yet for Atlas. The signal strength that they would obtain if they assume all the branching fractions are as in the standard model, that the only thing that changes is the production rate, is a bit high, by about 2 sigma compared to the standard model. But 2 sigma? 2 sigma goes away every day. 3 sigma goes away every year, and 2 sigma goes away every year. This is not significant. CMS, again, it's a little more updated. They've even updated it more since then, but let me point out a couple things around this plot that are interesting. So, here's gamma gamma. Actually, before I even do that, note, so you don't get confused, this green line is not at 1. It's at 0.94. Sorry, it's at 0.8. This is a probability. It's at 0.8. 1 is slightly to the right of it. So the dashed line here does not correspond to the green line. The green line actually corresponds to the 1.43 number that they have. So they actually sit slightly lower than the standard model. For almost the same mass, so that difference isn't very important. All right, let's look at gamma gamma. So you notice there are 3 entries. Untagged, VBF tag, VH tag. What's that about? Well, they take their gamma gamma events, which they've broken up into all these different categories and put back together again. And in particular, they selected 2 categories of special interest. One was events that look like this. Now with gamma sound. That look like they might have been produced in vector boson fusion, which is what this is called. WW goes to Higgs, or ZZ goes to Higgs. So if you look at the detector from the side, what you're looking for is events that have a jet going off this way, a jet going off this way, and somewhere in the middle, two photons. There's a couple of very interesting things that I want to point out to you about this process from the QCD point of view, related to what I said last time. So this quark came out of a proton, as did this one. And when it goes off, the proton shatters. Same with this one. Now, what's coming out therefore is two proton remnants and a quark in each direction. And as you know from last time, there's some color strings connecting these things. Where is the color string connecting this quark? What is this quark connecting to? In this case, we know the answer. In general, it could be very complicated. But in this case, we know the answer. Can you see why? It's maybe easier to see if we think about it geometrically, rather than as a Feynman diagram. So let me draw it this way. So in comes our proton, okay, and this guy spits off a W, it's heading this way. Here's our other protons coming the other direction, and it has a quark which spits off a W, and they're going to collide in the middle of making Higgs. And then this quark keeps going, and so does everything else from this proton and everything else from this proton. Where's the color? Is there any color crossing here? We have two colorless particles colliding, two W's colliding, or two Z's. And we know it because we're making Higgs. There's no gluons involved in the there. So therefore, the color string, as this quark goes out, is connected only to the beam remnant that's heading in the same direction. And similarly, here. And that means this quark is going to give me a jet, and this beam remnant is going to give me lots of crap, and there'll be radiation in between. And there'll also be a jet here, and various jets down there, and hadrons that we don't observe very well, and so forth. But in the middle, nothing. It's going to be very quiet in the middle. How quiet? Exactly how quiet. We need to know that when we use this fact. And that's one of the problems, is actually showing just how quiet it will be in there is a source of a big uncertainty. But roughly speaking, we expect events that are from vector boson fusion not only to have two hard jets, two jets that are in opposite parts of the detector with a large invariant mass of the pair and relatively low transmission momentum. We also expect there will be no jets in between them as a function of eta. So if this one has eta of 2 and this one has eta of -3, between those two regions we don't expect any significant jet activity to some approximation. So we'd like to say, well, let's just veto on that. If we see any jets between these two candidate jets that we see in the detector, we'll just throw the event out. Well, the problem is you need to calculate the background to doing that. You need to calculate what is the effect on a QCD background of throwing out jets like that. That's the hard part. Or even on the signal. So it's not as easy as it sounds. But in principle, we could try to look for two of these jets, look for quiet activity, and say, okay, that event probably comes from VDF, and that's kind of the sort of things they're doing here. I don't remember exactly what they did. I think they just demanded the two jets. They don't put a VDF, but I could be wrong. Some of these events actually come from other processes. They may come from glue goes to Higgs. and they make up from QCD. But anyway, they see an excess that's not consistent with 0. Okay. They're starting to check that this process actually occurs, which is another test of the standard model. It's a way of checking this coupling constant. If the standard model is correct and the Higgs gives mass to the W's, this process has to be there, and they're starting to see something. Okay, and then here, you can guess what that is. They're looking for signs of 2 photons along with the W and Z. All right, and there the data isn't very significant yet because the rate is smaller, but they're looking for it. Any questions? So it's not just a matter of checking the decay rates, it's a matter of checking the production processes. Unfortunately, production processes look different, so you can separate them. Let's see, so for Z's, they've separated 0 plus 1 jet, which is mostly glue-glue, from 2 jets, which has both glue-glue and vector boson fusion, and again you see that they're starting to be able to distinguish maybe that there's vector boson fusion in the intervals. Complicated to do that. In taus, they've tried to separate it. In W's, they've tried to separate it. Well, most of this isn't that significant statistically yet, but they're working. Okay, and then here's B's, where they've done VH, that is to say, they've done the one we discussed. And they're even trying to do TT bar H, but as you can see, they're a long way from having a signal. You have a TT bar plus an extra BB bar.
But I mean, Atlas is not able to do this kind of targeting.
Atlas is able to do it. CMS has been maybe a little more aggressive about doing these separations, and Atlas is taking its time. Some of these measurements have come out for Atlas. As I said, they haven't updated it. There's so many ways to cut and slice the Higgs data. There's certainly no way I can do it here. Both experiments have a very nice Twiki page for all of their, or the whole Twiki for all of their results. And they have a sub-page specifically for the Higgs. And so I encourage you just look up CMS Twiki public results or Atlas CMS public results, go to the Higgs sub-page, and look at the dozens and dozens and dozens of interesting plots. I can only pull out a few. And it's still being updated. They're still improving things. They're still making better measurements. It's always about improving the backgrounds so that you can see something more subtle than you saw before. Improving the method that you use so that you're less sensitive to this problem or that problem. And they're still doing it. You can argue maybe they're working too hard because they're going to get a whole bunch more data, and maybe it'd be better to kind of leave this for now and focus on looking for more subtle things in other processes. So maybe there are still a lot of people working. Okay, I found this plot, I could not find the source, I remember seeing it, I'm not sure who made it, and it's not entirely updated either. But this is just to sort of give you a sense for where we are, roughly. We have measured the coupling of the Higgs W's and Z's to tops indirectly, if you assume the standard model, through the loop coupling, which gives us glue-glue and gamma-gamma. And we've got some measurements of tau and B. And at least at the one signal level on this log plot, we're starting to see that, Higgs couples to mass, roughly. Okay. It's even more subtle than it looks because the couplings are not literally proportional to mass because in the case of the W and Z, there's a factor of a 1 squared 2 floating around. So it's not, it couples proportional to mass and the 2's are in the ring. And of course, the most important here is this. Okay, this is a Higgs boson. Especially one. Pick any one, any third one you kind of convince. It's roughly the standard model Higgs. The standard model like Higgs. Could things be different at the 10, 20, 30, even down here maybe the 40, 50% level? You bet. There's plenty of room for other things to be going on, but we are entering our precision measurements. Any questions about the Higgs? It's pretty much all I'm going to say about the standard model like Higgs.
What about CC bar?
CC bar is a very difficult measurement. There are some tricks that have been suggested, but it's not a near-term thing. You can ask me about it later and I'll see what I remember. It's not near-term. The only other one which is easy to understand how you might do it is Higgs goes to mu mu, which is just really, really small, so you need a huge amount of data, but it will be done eventually. I guess one other is Higgs goes to Z gamma. That's also hard, but it will be done eventually. Here's a plot which I think is really nice to look at, because it gives you two very important pieces of information. First of all, it gives you a sense for all of the different electroweak and Higgs-related and top quark-related processes that people are checking. In this case, it's just checking the rates. But of course, you can check other things that adjust the rates. But let's look at it. So what is this? This is the production cross-section in picobars. For everything from W production down to some of these Higgs processes, or here's a gamma goes to WWs down here. We haven't actually measured that yet. This is W. So let's see. So what are we looking at? So blue lines are the 7 TeV prediction. Green lines are the 8 TeV prediction. Open circle is a 7 TeV measurement. Closed circle is an 8 TeV measurement. You notice that a lot of the 8 TeV measurements aren't on there yet. It's because if you're making a precision measurement of a production cross-section, it takes a while to make sure you've got it all right. And people who do these measurements work very hard. So it's going to be a while before we see all of this. But at least there's quite a few of the measurements which have been done. At 7 TeV, they've all been done pretty much. And 8 TeV, there's a few of them. And so this is W. W plus 1 jet with some definition they don't put on the spot, exactly how much momentum that jet has to carry before you count it. 2 jets, 3 jets, 4 jets. These are the standard model predictions from the theory, okay, which is telling you how good theory is now, and how good experiments. Here it is for Z. Z plus 1 jet, 2 jets, 3 jets, 4 jets. Here you can start to see the error bar in the theory, right? It's still pretty small, and it's smaller than the experimental error bar, but again, this is 7 TeV, at 8 TeV there's more data. So the error bar at 8 TeV will eventually be smaller. This is telling you the QCD calculations, because this is really key. I mean, yes, there's electroweak physics in there, but it's mostly QCD, it's mostly jets, have really entered a golden age in terms of what we can do. You would not see clocks going out to 4 jets. Probably wouldn't see them going out beyond 2 jets. And even then, they probably wouldn't work so well at the teletron. This is really recent advance that makes it possible to see it. Here's TT bar at 7 and 8 TeV. The difference between the two was correctly predicted. And TT bar plus 1 jet, 2 jets, 3 jets. Here you see the error bars much bigger. It's much harder to predict experimentally. I'm sorry, theoretically. But within the errors, it's working. It's sort of interesting that the slopes here are very similar. I mean, of course, it is a log plot, but it's not surprising that Z and W would have similar slopes, right? All you're doing is exchanging one electron particle for another. TT bar, the slope is not the same, but it's interesting. It's sort of constant. Adding an extra jet, we have found various regularities that aren't deeply understood. But in QCD calculations, what you've often found is that adding an extra jet drops you by a factor, and adding an extra jet drops you by roughly the same factor. And it's true with TT bar as well. It's not the same factors for Z, but again, it's 0 to 1, 1 to 2, 2 to 3, it's kind of the same factor. And there are other regularities too that we don't understand. This is single top production. Sorry, this is this is single top production. We produce 1 top quark at a time. Here's a top quark produced with a W. Here's TT bar Z. Here's W plus photon, Z plus photon, W plus W, W plus Z, Z plus Z. I mean, it's amazing. And again, it's good to look at the numbers, right? 10 to the 5 picobars. With a total of 20 inverse femtobarns is 10 to the 9 W's of water. Okay, so we made a billion W bosons. We made a big, that's, and that's W goes to lepton plus neutrino, so it's even more W's than that. How about Higgs bosons? Well, here's the Higgs boson cross-section, and that's in the 20 picobar range. That means we made last year at Atlas and separately at CMS 400,000 Higgs bosons. Making a lot of these things. It's kind of remarkable that if you make 400,000 of anything, that it takes so long to find it. It's good to remember that given what the Higgs mass actually is, the CDF and D0 detectors, at the CDF and D0 detectors in Fermilab, 10,000 were made. Still couldn't find it. This is partly to tell you that stuff can hide. I think Raman made this point as well. Stuff can hide. We could be making thousands of some new particle and not know it's there. This is when we even knew how to look for it, and it still took it. From 1989, from when the first Higgs boson was produced at the teletron, till 2012, when it was finally discovered a different machine. Okay, so, and more or less things are working for the Higgs too. Okay, now, the standard model works beautifully, and what's wrong? Well, there's so many different ways it can be wrong, and it's really hard to have a coherent discussion about this, but I'm going to do my best to throw some things out at you, which is really all I can do. I mean, there's no way to organize a discussion of everything that could change in the standard model of the system of data. But I want to start with the simplest possible thing, which is I'm going to take the standard model and add one new particle. Literally 1 degree of freedom. There's only a way I can do that. I'm going to add a scalar particle, which is real, not complex, and carries no standard model quantum numbers at all. And I'm going to add it to the standard model in the only way that's allowed, preserving normalizability. And let's just work out the consequences. There can't be too many, can there? Pretty simple. Okay. So, we'll take a field S that's real, and it's an SU3 cross SU2 cross U1 singular. And we'll take the Lagrangian to be the standard model Lagrangian plus anything that's allowed by gauge invariance. What's allowed by gauge invariance? Well, higher dimension operators, there's lots of those. I can take any operator with standard model multiplied by S or S squared or something. What's allowed that's also normalizable? Think about the structure of the standard model. Which couplings are not dimensionless? Because if a coupling is dimensionless, it multiplies something's dimension as 4, and then I can't put an S in front of that. So which couplings are not dimensional? So which couplings are dimension full?
Mass of Higgs.
Mass of the Higgs, anything else? No. That's why the hierarchy problem has to do with mass of the Higgs, nothing else. It's because dimensional analysis fails, remember? And dimensional analysis can only fail if you have a dimension, and the place where it fails is... That's not maybe the best way to say it. The reason we got a problem with the Higgs mass is it should be up the Planck scale. It's the only thing that should be up the Planck scale. It's the only thing you put the Lagrangian has a mass in it. So we can have S H squared, and we can have S squared H squared. Let me keep things simple and just assume that S either has an exact or, well, let's assume that S has an exact C2 symmetry, so we'll add that in. So there's a symmetry here which forbids this term, just to keep things simple. Okay, and then of course, I can still have an S to the 4th term. Okay, and then there are coefficients here which, you know, you can give them some funny names. You won't really pay much attention to what the names are because we're not going to calculate things in detail. So my question to you is, what can this theory do? Simplest extension of standard model. What can happen? Well, one thing you notice right away is, well, it's going to depend on whether S gets a bev. So we better separate it into the case where S is 0 and S is not equal to 0. And whether it's 0 or not is going to depend on, you know, something, you know, it's going to involve that coupling, for example. If it's negative or positive, or how negative it is, and so forth. Right? If H can get a bev, S can get a bev. No obvious difference. So, all right, well, let's focus on this case first. That doesn't seem too bad. So if S is equal to 0, what can you tell me about S? What does S decay to?
Higgs.
Today?
Higgs.
S decays to Higgs. Wrong. Okay. It's stable. It's a Z2 symmetry. Z2 symmetry is not broken. S is stable. Hey, it's a dark matter candidate. Well, maybe. Okay. If S is equal to 0, then because there is a Z2 global symmetry, a new symmetry, it's not present in the Standard Model, we have the potential for a new stable particle. Whatever is the particle, the lightest particle, carries this exact Z2 symmetry. It's important to be exact, of course. If it's not exact, it will decay. Right? And Z2 is preserved, and S is stable. And since it doesn't carry any Standard Model quantum numbers, it's even more invisible than a neutrino. It's as invisible as a right-handed neutrino. Well, then who cares? Do we care? Oh, we care in a big way. We cared much, much more before last year. No, the year before. So the S can't decay to anything, but can anything decay to the S? Let's see, once the Higgs gets a VEV, what happens to this term? Once the Higgs gets a VEV, this term becomes V squared plus 2B times the Higgs plus H squared S squared. Okay, I'm leaving out factors of square root of 2 that don't matter much. The important thing is, this term contributes to the S mass. This term is linear in H, and it allows H goes to SS. So if the numbers work out such that S has a mass that's less than half the mass of the Higgs boson, the Higgs is going to decay to S pairs, which are invisible. All right, so suddenly we have invisible decays of the Higgs. Well, in the Standard Model, we have Higgs goes to ZZ, where Z goes to neutrinos. But that's a small process. Right? So we do have invisible decays of the Higgs in the Standard Model. This is a process that's controlled by a new coupling constant. This coupling doesn't have to be small. The effective coupling here doesn't have to be small. So here's where it's really important, what I told you a couple times ago, about the Higgs width. Right? The Higgs width is very small. That all of the Higgs decays are suppressed. They're suppressed by the bottom part Fukawa coupling, or they're suppressed by the fact that W and C have to be on a shell, or they're suppressed by the fact that gamma-gamma comes through a loop. So the Higgs width is about 10 to the minus 5 of its mass. Now here, if I have something like this, and the S is on shell, there's no suppression factor. It's just determined by this coupling. Why shouldn't that coupling be moderate? Even if it's 10 to the minus 2, you square it, it's 10 to the minus 4, it can give you a branching fraction of the Higgs to an invisible final state, which is 99%. And suddenly, you don't see this thing. One new particle can ruin your whole day. You build this whole LHC, you head out to measure all the Standard Model cross-sections and branching fractions, and suddenly you discover that you're in Higgs just because of one new particle. 99% of the time it decays invisibly, and everything you were looking for is suppressed by a factor of 100, which means you need 10 to the 4 times as much data typically, and you're on. And until 2012, you were just kind of hoping that wasn't going to happen. Because if it can happen in theory this simply, you can imagine how many other ways it can happen. It didn't happen. We've got a nice Higgs. It's sitting there at Standard Model light. But if I can make it 100% of the time decaying invisibly, I certainly could make it 10% of the time decaying invisibly. And this could be the most important thing to discover, because this could be the particle which lies beyond the Standard Model we can actually access at the LHC. And it's sitting in a very difficult measure. How do you discover the Higgs decaying invisibly? This leads to a generic set of problems at the LHC, which we will discuss in great detail starting at the beginning tomorrow, which is, there's a lot of things that could be invisible at the LHC, like dark matter. We might be producing dark matter. How do you figure that out? You don't see it. Well, you still need some methods. And of course the method is you look for the things you're producing along with the dark matter, or the things that decay down to the dark matter, producing something else along the way. You need a technique. And we have a technique for invisible things, which I'll discuss. And then we'll worry about this case. So, homework, for anyone who's so inclined. Think about this case and figure out what happens. It's not that hard, but it's really interesting. Okay, and then tomorrow we'll get as far with this and some other Higgs things we would look for in the context of Higgs, and then also hopefully time will permit some discussion about supersymmetry and top primes, which obviously I'll do very briefly, but enough to give you a feel for the breadth of different types of things that one tries to do with this machine.